that. All right, lights blinking. The textbook introduces the generalized form of Ampere's law in chapter 31. I'm going to wait and introduce that after chapter 32. Yeah. Officially, I'm going to do it sort of slightly out of order. I'll do 32, then I'll sort of do 34, and then we'll jump back to 33. Based upon what we've done so far in the course, what do you suppose that is?
Magnetic flux?
Yes, it is.
Sorry, so this is chapter
32. So phi dot dA, we touched on it potentially briefly when we talked about Gauss's law of magnetism and the fact that the total magnetic flux through any closed surface is 0. But we're going to be dealing less with the closed surface, more with an open surface. Now, so Faraday in the, I think it's the 1820s, was playing around with this, and what he noticed, he had a loop of wire here connected to an ammeter, basically something measuring current, probably more specifically a galvanometer, but good enough. And he had battery hooked to, there was a switch and another wire. And he noticed, now I don't think this was an experiment, it's always, the way I've always read it, it's always been sort of an accidental discovery as opposed to he was testing this at first. But he noticed that when he closed this, the needle here would twitch. It would twitch to something and then it would go back to 0. Then when he disconnected it, it would twitch the other direction and then go back to 0.
So it's like once charges started moving and stopped?
Yes. More specifically, well, then he played around with it, but what he was noticing, it's the fact that the moving charge creates a magnetic field. So but it wasn't the magnetic field itself that was causing it, it was the way he was sort of experimenting. It came across like it was the change in the magnetic field. But then if you can play around with that, we can look at various structures here. That doesn't get the same result as that did, or putting it here, you got a different result. Even though the magnetic field was the same-ish. But what he noticed was that there were two things that were affecting it. It was the change in the magnetic flux, thus the reintroduction of this. And he realized that the magnetic field he was created a magnetic flux through this area right here. So the change in the magnetic flux with respect to time seemed to induce a voltage, which therefore caused a current. Now, what Faraday realized is that there was a connection there. About the same time, Lentz, and I cannot think of his first name, I think a Russian physicist or scientist, came up with a more mathematical formulation, basically that. Now, a lot of textbooks make it come across like what Lentz provided was the negative sign. I think historically what Lentz provided was the math. The concept came up was Faraday. This is the last full, this is one of Maxwell's equations. I was about to say it's the last one, but we still have that second piece of Ampere's law. This is known as Faraday's law, although I will sometimes refer to it as Faraday-Lentz's law because they both, I think they both deserve some credit into it, but textbooks generally call it Faraday. Give credit to Faraday. So all I need is a change in magnetic flux, and I create a voltage, and an EMF. Again, this is the symbol for an EMF. This is not the permittivity. This is the epsilon for EMF. Now what the minus sign is indicating is realize that in my circuit here, I make the connection, suddenly I create a current, which creates a magnetic field, which creates a magnetic flux through this, which creates a current. Nature is not going to have this runaway process. I'm not going to be able to create a current here, because as soon as I create a current here, it creates a magnetic field, which creates a magnetic flux through this. The current from here is not going to create a magnetic flux here, which is going to make this magnetic flux suddenly bigger over here. It's not going to get into this cyclical thing where I can suddenly get this, I get this current going, which gets that current going, which makes this current bigger, which makes that current bigger, which makes that current bigger, which makes that current bigger, and suddenly the whole thing blows up. If nature worked that way, we probably would have destroyed ourselves as a species long ago.
We'll get there.
Pardon?
We'll get there.
Yeah, well, you know, there's hope yet. Actually, I might go so far as to go, if that's the way the process worked, then I don't think any species would have ever shown up. Okay. So what the minus sign is telling us is that the EMF here that's created is going to be designed to offset the change in the flux. So it's going to try to dampen it. And my nose is itching really bad right now, so excuse me. Let the camera focus in on that board there. Speaking of itching noses, any of you raised with the superstition of what it means if your nose itches?
I always wonder like why we itch, but not superstition of it.
Oh.
What is
What is
I was told growing up that means you're going to kiss a fool. But maybe there's something mom made up.
Do you know what causes us to itch? Like,
It's a mild form of pain, isn't it?
No, well, I'm not sure. I never figured it out, like why we itch.
Your body telling you something's wrong.
Yeah.
I don't know, any?
Yeah, I think it's because something is like I feel like it's the same for when you cough. So like there's something trapped in the mucus, and then it just wants to get rid of it. So it's like your body telling you to like get rid of it.
Mild irritation.
I think I see the point. I feel like it's like one of our little hairs coming in contact with like a particle or something.
Should have done the dots. And so on. So basically I've got a wire here. This is a bent piece of wire. And you'll notice there are a number of problems where I try to describe this out in words, but basically it's a bent wire problem here. And then on top of that, we have a separate wire. So what's now the blue wire can easily move on the open rectangle. And it can slide. We have a magnetic field, and we'll just use nice numbers, 3 Tesla. At some point today, I will make the Princess Bride reference. If you have not seen the Princess Bride, shame on you. This wire right here, well, let's just deal with it conceptually at first. So all I have are these wires here. There's no current flowing whatsoever. This wire is just sort of sitting there. As I move this wire outwards at some speed v, let's follow the train of thought. There's some magnetic flux flowing through this wire. Apparently did not get rid of whatever was causing it. So as this wire moves out, my magnetic field stays the same, but the area increases. And again, this is my area right here. So my magnetic flux is increasing. If my magnetic flux is increasing, I have a change, and therefore I induce a voltage or an EMF in this wire right here, and basically because I can have a complete circuit, and therefore I will create a current. So the question is, which way is that current going to flow? So my magnetic flux, is it increasing or decreasing as the wire moves out?
Increase.
And the induced current is going to try to stop that. It stops whatever the change is. So if I have a wire right here, and I have a current flowing through it, sort of a separate thought, it'll connect. If my current flows this way, which way is the magnetic field in the center? Right hand.
To the page?
Sorry, into the page? Is that what you said?
Yes.
Yeah, it's in the board. Right hand rule, current's flowing around like that. My magnetic field is going into the board. If my current is flowing the other direction, yep, it's coming out. Since my magnetic field here is, my magnetic flux is increasing, it wants to try to stop that. There's basically two ways to stop an increase in the flux. I can either decrease the magnetic field or decrease the area. Potentially do both, but it's not going to happen. The current that is induced is going to try to oppose the magnetic field, because it's not going to make the area smaller, because I'm mechanically making the area bigger. So it's going to induce a current that is flowing counterclockwise. Because this current is going to create a secondary magnetic field, which is in the opposite direction to the external magnetic field. If it created in the same direction, sort of tapping on to what I said before, if the current went the other direction, it would increase the magnetic field in here, which increases the magnetic flux, which increases the EMF, which increases the current, which increases the magnetic field, which increases the magnetic flux, and so forth, and you get a runaway current. Free energy is not happening. There's another way of looking at this. If I think about this wire right here, if the wire's coming this way, remember that if I've got, when we had the current flowing in opposite directions, it puffed out. Because this creates a magnetic field that's going into the board here, out of the board here. This creates a magnetic field that's going into the board here, out of the board here. In other words, we get a boost in the magnetic field in the middle, and we get a lessening of the magnetic field on the outsides, and the wires will move towards the weaker magnetic field. So if I think about just this wire, as this moves out, it wants to move back towards the middle. It wants to decrease the area. It's not going to, but it wants to do it. So it's going to create a current that weakens the magnetic field on the inside. So current's going to have to flow that way so that my magnetic field will be into the board over here, out of the board here. Just a different way of looking at the exact same thing. So if the current is now flowing up this wire right here, that means it's going to have to flow counterclockwise. So let's actually do some math here. Let's make this 2 meters per second. Let's make this 4 meters and make that 5 meters. My magnetic flux is going to be my magnetic field. Let's do it all formally for right now. No. Oh. Recognize I'm taking an integral and then a derivative of an integral, but they don't cancel each other out because this derivative is with respect to time and the integral is with respect to area. There are 2 different quantities involved. My magnetic field is constant, so it can come out. My magnetic field is in dot dA. Why don't I just make into the board the direction of my area vector so that my flux is positive. So into the board is my positive direction. I'm sorry, into the board. We'll make my positive direction. So this just becomes B integral dA, which is just B times A. So now my induced voltage, or the induced EMF, becomes negative dVA dt. My magnetic field is constant, so the derivative, that just pops out, so negative B dA dt. And area is just length times width, so this is negative V d length times width dt. And we'll make let's make this one length and this one width. Actually, I want to make this one length and this one width. And the reason's going to come up in a bit. So my length is constant in my particular drawing right there. The length comes out. So this becomes negative VL dW dt. Just the change in width with respect to time. And what is dW is a width here. It's some distance from here to here. What is dW dt?
V is at velocity.
Indeed it would. And the negative sign, generally I don't write the negative sign. It is here, but again, the whole point of the minus sign is to indicate direction, and we've already thought through the direction. We know what the direction is of the current. And so this is known as motional EMF. Because we're creating a voltage just by moving. And this is the Princess Bride reference. When Wesley is being helped by Billy Crystal and pumps the air in, he goes, and what Billy Crystal here is the bleb.
We don't care about the length, or did it cancel out?
No, we do care about the length. We actually come up with a number here. So my induced EMF.
So that's it, right there in the middle.
Yeah.
Oh yeah, that's.
I thought you were dividing.
Oh no, that's bleb. Who hasn't seen Princess Bride? I appreciate your speaking up, but you really do need to watch the movie. You really do. If you've ever watched honest trailers where he rips apart every movie, except not Princess Bride. He starts to and he says, no, I can't even rip this one apart. People who've seen it, agree?
What's it called?
Princess Bride.
It's, if you have Disney Plus, I think it's under there.
Yes.
So, what was that, Trevor?
If it's on, if you have Disney Plus, it's on there.
Oh, okay. Even there was one particular class where I said, I'm expecting you to, I think it was a summer class. I expect you to watch this movie. And then I had extra credit questions on the last test.
The entire last test is just going to be a Princess Bride test.
I started earlier with that group though, not with the one through though. All right, so my EMF is going to be, just looking at the magnitude of it, 3 Tesla times the length, this distance right here, 5 meters, times the velocity, 2 meters per second.
That should be 30 Tesla's meters squared per second.
Or commonly known as
Volt.
and thus we have a new unit of time. A second would be a Tesla meter squared per volt. Now I know what you're thinking. You're going, oh, that's great, but where's the calculus? Because this calculus just has some constants in it. All right, let's do it. Questions before I erase it? Oh, that'd be dropping off the grid. So I have some current flowing through this bottom wire. Let's get, so it's infinitely long. Let's give some dimensions here for this other square. So how about 0.5 meters? 0.9 meters, 1 meter. What is the induced EMF in the rectangle? I have a current that is changing, which means my magnetic field will be changing, which means my magnetic flux will be changing, which means I'm creating an EMF. I'm not going to worry about the signs, other than we will think through it. If my current is flowing to the right, what is the direction of the magnetic field here?
Coming out of the board.
Right hand. Right hand rule. So I've seen a number of people doing right hands. Are we sticking with what Austin said? Or do you want to question its lineage? Neither, apparently.
The current's flowing which way?
Current's flowing. Current is flowing to. Oh, did I say to the right?
Yeah.
Oh. Yeah. Flowing to the right. Flowing to your left. The direction of the arrow. So it's
On the board.
so right hand current's flowing in this direction, so the magnetic field it creates in out. Here it's going into the board. I don't want to make it seem like it's only in that space. It's all over, and then it's coming out over here. Now, a number of people said it was coming out of the board, not into the board. What was the?
I think I did my thing wrong.
Yeah, I did it wrong.
Okay.
Can you do that again?
Yeah,
So you did.
So-
can you do that right here? Walter?
All right. So, in the case of a magnetic field created by a current, it's like you're hitchhiking. Thumb in the direction of the current flow, or the positive charge flow, or opposite the negative charge flow. Current's flowing this way. My hand into the board, out of the board. Over here, it's going up. In the bathroom, it's going down.
So you aim your fingers towards where you want to see where the magnetic field is going?
Yes.
Okay.
All right, so my magnetic field is going into the board here. Since my current is increasing, because as time goes on, this number will get smaller and smaller, so it approaches 3 amps maximum. So my current's increasing, magnetic field is increasing, and so it starts at 0, current increases, magnetic field increases. But the rate at which, this could be an interesting problem. So just on the surface of this, if we just say the magnetic flux is increasing here because the magnetic field is increasing, suddenly something popped into my head. I'm trying to resolve it. Okay, I'm back. Which way will the induced current be in the rectangle?
Clockwise.
Why?
Well, there's nothing affecting, well, there is something affecting the magnetic field, but the magnetic field at that portion is into the page, and when it's into the page, it flows counterclockwise.
Is it counterclockwise?
Clockwise.
Clockwise. So if the current induced in this is clockwise, where will the magnetic field that it creates be? Which direction will it be in?
Into the board.
In the same direction as the magnetic field created by this.
No.
So, oh wait, clockwise. So Mario was saying that the current's going to be flowing this way. That will create a magnetic field into the board in the center, which helps the change. It basically increases the magnetic field, and nature hates that. The induced current will try to oppose the change. So the current has to be flowing counterclockwise.
Oh, I see. So it'll always flow in the direction opposite of like the magnetic field that's already there. That's already like created.
Yeah, it opposes the change in the flux. After this one, well, remember, or more likely I'll do another example and then remember when it actually might be in the same direction as the magnetic field. All right, so it's going to be counterclockwise. Let's actually get into the math. So not worrying about the sign here. We have d phi b dt. I know phi of b is the integral of b dot dA. My area is the area that the magnetic field is going through. This is the one in question right here. There's my area. My magnetic field is not constant throughout this whole thing. The magnetic field is stronger closer to the wire than it is farther away from the wire. Matter of fact, what is the magnetic field coming from an infinitely long wire?
0. Is it 0?
No, I was looking for a formula.
Mu sub naught I divided by 2 pi r.
That's the magnetic field coming from an infinitely long wire. Now you'll notice that I suddenly did away with the vector aspect of it. It is a scalar product between B and dA. My area is, the rectangle is flush with the board. That means the area vector is either pointing out of the board or into the board. My magnetic field is into the board, so my dot product is either positive or negative, but I've dropped off all the negative signs just to avoid that hassle. And we've already thought through the direction of the induced current. So I'm not worrying about whether since they are either parallel or anti-parallel, that means it's going to be just the magnitudes multiplied together and the directions either and ultimately positive or negative. So what's question?
Yeah, what's mu again? I know it's like specific to the magnetic field.
Permeability of free space.
What's the difference between permittivity and free space?
Permittivity is how a